Welcome to this technical overview of the AUTOSAR Communication Stack, Comstack. In modern vehicles with many electronic control units, ECUs, Comstack provides the infrastructure for reliable data exchange. Its main goal is to offer a standardized interface that hides the complexity of different communication protocols like CAN, LIN, and FlexRay from application software. This modular approach allows application signals to be transmitted across different bus systems without modification. This page introduces the vertical integration axis, illustrating how data moves from the application layer through service and abstraction layers to the physical hardware, ensuring reliable real-time communication. The key value of the AUTOSAR Comstack is separating functional software from the physical hardware. In older automotive systems, application code was tightly linked to specific bus technologies, so switching from something like CAN to automotive Ethernet often required major software changes. Comstack removes this dependency by letting the application layer work only with signals and values, such as a vehicle speed of 100 km per hour. The lower layers then convert these signals into protocol-specific data like CAN frame IDs or Ethernet packets. This separation improves software reuse across different vehicles and hardware platforms while keeping applications independent of the underlying communication technology. To achieve this abstraction, Comstack utilizes a strict layered software architecture divided into three main levels: the application layer, the runtime environment, RTE, and the basic software, BSW. The BSW is further subdivided into the services layer, the ECU abstraction layer, and the microcontroller abstraction layer, MCAL. At the top, the application layer contains software components, SWCs, that focus on functional logic. The RTE acts as the central intermediary, providing communication services that hide whether data is moving locally within a single ECU or across an external network. Within the BSW, the services layer provides bus-independent management. The ECU abstraction layer offers standardized interfaces for bus-specific modules like CAN-IF or LIN-IF, and the MCAL contains the low-level drivers that have direct, register-level access to the microcontroller's communication peripherals. In this section, we examine the metamorphosis of data, which describes the fundamental evolution of information as it descends through the AUTOSAR communication layers. Communication begins at the application level in the form of a signal, representing a single functional value like a door status or temperature. As this signal enters the service level, the COM module performs the first major transformation by packing multiple signals together into an interaction layer PDU or IPDU. This transition is a critical boundary. The signal-oriented interface used by the application ends here, and the data is now managed as a protocol-independent payload ready for routing. If the data block is large, such as a diagnostic message exceeding 8 bytes, it moves to the transport level, TP, where it is transformed into a network layer PDU, NPDU. At this stage, the TP module adds headers for segmentation and network addressing, breaking the data into smaller parts if necessary. Finally, at the driver level, the data is encapsulated into a data link layer PDU, or LPDU. This final version includes a hardware header and a CRC, cyclic redundancy check, for error detection, making it ready for physical transmission over the bus. The vital concept to remember is that the PDU name changes at each layer to reflect the addition of protocol control information, PCI, which acts as the instruction manual for lower layers to correctly handle the data. The AUTOSAR COM module is the topmost component of the Comstack, positioned directly between the RTE and the PDU router. Its primary role is to act as a signal packer, transforming signal-oriented data from the application into protocol data units, PDUs, for network transmission. During transmission, COM bundles multiple individual signals, the smallest entities of information, into an interaction layer PDU, IPDU, based on a configured layout. It also manages complex tasks, such as endianness conversion between Big Endian, Motorola, and Little Endian, Intel, formats to ensure data consistency across different processor architectures. Additionally, COM implements filtering mechanisms, transmission triggers, pending/triggered, and deadline monitoring to enforce timing requirements. This module is essential for optimizing network bandwidth and ensuring that time-critical data is delivered within the required system deadlines. The PDU router, PDUR, serves as the central switching station of the communication stack, managing the routing of PDUs between different modules. Unlike a dynamic IT router, the PDUR operates based on a statically defined routing table established during the system design phase using AR/XML configuration files. The module is protocol independent. It simply identifies a PDU by its unique ID and forwards it to the correct destination. PDUR operations include down-routing transmission requests, up routing reception indications, and gateway routing, where it moves data from one bus system to another, such as from CAN to LIN. To maximize efficiency, the PDU-R supports zero-cost operation, where it can be optimized to act as a simple macro layer, directly calling lower-layer functions to eliminate the processing overhead of a full routing engine. To understand the COM stack in motion, we must examine the transmission flow, or TX path. This is a request-based process that moves data from the top layer down to the physical hardware. It begins in the application layer, where a software component updates a functional value and sends it to the RTE. The COM module then packs this signal into an IPDU and issues a transmit request, typically using the PDUR_COM transmit API. The PDU router identifies the correct routing path and forwards the request to the bus interface CANIF, which adds necessary protocol headers. Finally, the request reaches the MCAL CAN driver, which writes the data directly into the microcontroller's hardware registers, physically placing the bits onto the vehicle bus. This strict flow ensures the data is packaged and sent with high reliability and predictable timing. The reception flow, or RX path, is an indication-based process that moves data upward from the physical bus to the application. It starts when the hardware controller receives bits from the network, triggering an interrupt in the MCAL CAN driver. The driver then notifies the bus interface, CANIF, via the CANIF_RX indication callback. CANIF performs essential validation of the identifier and data length code, DLC, to ensure the message is relevant to the ECU. Once validated, the message is sent to the PDU router, which routes it based on its PDU ID to the COM module. COM then performs the critical task of unpacking the IPDU into its constituent signals, handling any necessary byte order conversions. Finally, the RTE provides these updated functional values to the application layer software components for processing. In the AUTOSAR Communication Stack, the Transport Protocol TP layer is a critical intermediary positioned between the PDU router, PDU-R, and the bus interface such as CANIF. Its primary mission is to overcome the physical limitations of standard network frames, most notably the 8-byte payload limit of classic CAN. While the application layer often needs to transmit large blocks of data, such as UDS diagnostic messages or software flashing routines that require kilobits of information, the physical bus cannot handle these in one go. To solve this, the TP module implements a standardized protocol, such as ISO 15765-2 for CAN, to manage segmentation and reassembly. The metamorphosis here involves breaking a large IPDU from the PDU router into multiple smaller network PDUs, NPDUs. A segmented transmission typically begins with a first frame, FF, which informs the receiver of the total message length. The receiver then responds with a flow control FC frame, which acts as a traffic cop by defining how the rest of the data should be sent. Key parameters exchanged here include the block size, BS, which determines how many frames can be sent before another acknowledgement is needed, and ST-min, separation time, which defines the minimum interval between frames to prevent buffer overflow. Following the handshake, the sender transmits the remaining data using consecutive frames, CF. On the receiving side, the TP module is responsible for reconstructing these segments into a single cohesive message. Throughout this process, the TP layer monitors vital timing parameters, such as N_AS assemble time and N_BS block size time, to detect communication errors or lost frames. By abstracting these complex coordination tasks, the transport protocol layer allows the upper application layers to handle large data transfers with the same simplicity as a single frame signal, ensuring reliability and data integrity across the vehicle network. Focusing on the CAN stack implementation, we see how specialized management modules coordinate to handle the most common automotive bus. The CAN State Manager, CAN-SM, implements the control flow for the bus, managing procedures like startup, shutdown, and the recovery from critical errors such as bus-off conditions. Working alongside it, the CAN Network Management, CAN-NM module, coordinates the transition between normal operation and bus sleep mode across the entire network cluster. These modules interact with the Communication Manager, COMM, to ensure that the ECU transitions into power-saving modes when communication is not required. This hierarchy of state and network managers ensures that the CAN network is synchronized, energy efficient, and capable of recovering from bus errors in a standardized and predictable manner. In this section, we explore the LIN and FlexRay variants of the AUTOSAR Communication Stack, which serve as specialized alternatives to the standard CAN bus. While CAN is the backbone of the vehicle, LIN, Local Interconnect Network, is utilized as a cost-effective single-wire solution for subsystems where high bandwidth is not required, such as mirror adjustment or power seats. LIN operates on a strict master-slave topology, where a single master node controls all bus access through an active scheduling mechanism. A defining feature of the LIN stack is the schedule table, managed by the LIN-IF-LIN interface module. This table contains a sequence of items defining which frame ID should be sent at what time, ensuring that the network remains collision-free without being event-driven. The LIN-DRV LIN driver serves as the base layer, providing direct hardware register access to perform physical transmission. On the opposite end of the performance spectrum is FlexRay, a high-speed, 10 megabits per second protocol designed for deterministic, fault-tolerant communication. FlexRay is essential for safety-critical X-by-wire applications, such as steer-by-wire or advanced ADAS systems, where data must arrive within microseconds of a predicted time. The protocol is characterized by a fixed-duration communication cycle, meticulously divided into segments: the static segment for time-critical deterministic data using TDMA, the dynamic segment for event-driven traffic, and the network idle time used for essential clock synchronization. Because FlexRay is time-triggered, it requires strict synchronization across all nodes in the cluster. Within the stack, the FRIF FlexRay interface module manages the alignment of PDU transmissions with their assigned slots and cycle offsets, while the FRDRV FlexRay driver handles the register-level interactions with the internal or external FlexRay controller. Together, these protocols allow the AUTOSAR Comstack to scale from simple body electronics to high-performance, safety-critical vehicle control. As automotive architectures evolve, the Ethernet stack has become vital for high-bandwidth applications like ADAS and infotainment. In this stack, the PDU router interacts with the socket adapter (SOAD), which is responsible for mapping traditional AUTOSAR PDUs to specific TCP/UDP sockets and IP ports. This layer enables advanced features like diagnostics over IP-do-IP and SUM-AIP, a service-oriented middleware that allows ECUs to call methods on other units dynamically. Unlike the signal-oriented nature of CAN, the Ethernet stack supports service discovery (SD), allowing ECUs to find services on the network at runtime. This architecture provides the flexibility required for software-defined vehicles, allowing for high-volume, secure data transfer while maintaining seamless integration with the legacy PDU-based parts of the Comstack. Network management (NM) is the cornerstone of vehicle power efficiency. Its primary goal is to save the car's battery by shutting down inactive buses synchronously across all nodes. The stack uses a standardized mechanism where nodes send periodic ring messages or bit vectors to indicate they are awake. If a node stops receiving these messages and its internal timers expire, it enters the prepare bus sleep state to ramp down operations. Once all nodes on the cluster agree, the system enters bus sleep, low power mode. A wake-up event, either from external network traffic or an internal request, will trigger the transition back to network mode for normal operation. This coordinated sleep-wake cycle ensures that the ECU consumes minimum power when the vehicle is stationary, or when specific functional data exchange is not required. The AUTOSAR Comstack is not just a data transport mechanism. It is a robust framework designed to maintain system integrity through sophisticated error handling and diagnostics. Within this architecture, errors are strictly classified into three primary categories to ensure proper handling throughout the software lifecycle: development errors, runtime errors, and production errors. The Development Error Tracer (DET) is the central hub for catching software-based issues early during the coding and integration phases, such as an invalid PDU ID or an incorrect API configuration. When a module reports a development error to the DET, the program flow may terminate or trigger an ECU reset to prevent unpredictable behavior. For field operations, the Diagnostic Event Manager (DEE) takes over, processing and storing diagnostic trouble codes (DTCs) and associated freeze-frame data when hardware-related failures, such as a cut wire or sensor failure, are detected. These events are stored in non-volatile memory for later repair actions in service garages. Complementing these is the Diagnostic Communication Manager (DCM), which handles requests from external diagnostic tools using standardized protocols like UDS, ISO 14229, or OBD. The DCM communicates through the stack to execute commands or retrieve system information to satisfy these diagnostic requests. Furthermore, the CAN State Manager (CAN-SM) implements a critical mechanism known as bus-off recovery. This state machine monitors the CAN controller's error counters and, upon reaching a threshold, disables the transmission path and initiates a recovery sequence to restore the node to a functional state. Finally, the Diagnostic Log and Trace (DLT) module provides a centralized service to gather log and trace messages from software components, converting them into a standardized format for external analysis via the PDU router. Together, these modules ensure the vehicle remains safe, maintainable, and capable of recovering from communication faults. We conclude with the strategic value of the AUTOSAR Comstack in the era of software-defined vehicles. This architecture is built on three core pillars: modularity, allowing hardware to be swapped without rewriting functional code; configurability, where behavior is defined in ARXML files rather than hard-coded logic; and safety and integrity, enforced through strict layering that prevents data corruption. As automotive systems move toward centralized architectures, the Comstack continues to evolve, integrating advanced security through secure onboard communication, SecOC, and precise timing via time-sensitive networking, TSN. Ultimately, the Comstack provides the standardized pipe that allows complex, distributed automotive software to function as a single, cohesive, and reliable system.